Modern theoretical physics computes exactly what happens once a local law is specified. Using Lagrangians and field equations, we calculate particle interactions with absolute precision. However, this success hides a gap in our understanding. We can trace the mechanics of a system perfectly, but the reason these specific laws, symmetries, and constants exist in the first place remains unexplained. Philip Lilien's closure framework moves to bridge this gap. The architecture seeks to derive the constants and symmetries of the universe through mathematical necessity, rather than inserting them by hand to match experimental observations. This requires a conceptual pivot known as the explanatory reversal. Traditionally, we treat local physical laws, like gravity or electromagnetism, as the foundational building blocks of reality. Lilien proposes that these laws are derivative residues. This diagram compares the two opposing directions of inquiry. The conventional approach on the left starts with measured local laws, building upward from observed parts to infer the global organization of reality. The generative closure approach on the right views local law as the stable, compressed form of a broader, coherent organization. Reality descends from a globally coherent space, contracting through a systematic restriction of possibilities. In this framework, the equations observed in our experiments are the terminal result of a deeper, rigorously structured cosmic restriction process. This framework defines lawfulness as compressed coherence. This compression refers specifically to a possibility compression operating on a dual admissible space picture. By removing admissible relational possibilities, the framework shrinks the set of states and transitions that can exist within the universe's constraints. The starting state, global nonclosure, represents a regime of highly coupled relational freedom. It is a state where multiple local realizations are still admissible before they are resolved into definite laws. The unyielding laws of physics are the invariant structures that remain after all other relational alternatives have been mathematically excluded. A direct jump from an unresolved global continuum to a rigid local equation is logically incomplete. There must be a transitional architecture that handles the emergence of definite law. The architecture utilizes three closure regimes. It begins with global nonclosure, where relational freedom is high. Next is partial closure, where restriction is graded. Finally, local closure, where possibilities contract into repeatable behaviors, reaching exactly one. This transition is governed by a strict mathematical engine, the continuous operator and its eigenvalue descent. In the partial closure regime, the singular spectrum of possibilities starts as a graded continuum. As the system undergoes continuous descent, the eigenvalues spread, separating into retained and suppressed channels. The descent terminates at absolute saturation, described by the saturated closure projection theorem. The singular spectrum locks to exactly 0 or 1, creating an orthogonal projection onto a stable fixed-point space. Local law is the invariant structure surviving this zero-loss projection. While this explains the engine of constraint, the framework must still account for the specific forces and particles of our universe. The standard model relies on three gauge groups, U1, SU2, and SU3, to govern the fundamental forces. However, it provides no explanation for why nature utilizes these specific symmetries. The closure framework identifies the automorphism groups of the invariants that survive the closure process. We find the symmetries required to protect specific geometric structures. This sequence shows how symmetries emerge as carrier space expands. On a one-dimensional complex carrier, the requirement to preserve a basic Hermitian norm naturally results in the U1 group. Expanding requirements to two complex dimensions forces the preservation of the Hermitian structure and a complex volume form. This yields the SU2 group. Imposing these same requirements on a three-dimensional complex space, preserving the Hermitian structure and a complex volume 3 form, forces the emergence of the SU3 group. This 1 to 2 to 3 sequence is a structural consequence of increasing carrier size. Each gauge force is the inevitable algebraic stabilizer required to protect the surviving invariants during compression. Ultimately, the forces of nature are the stabilizers required to maintain phase-spatial geometry under the pressure of closure. Matter itself is reconstructed within an SU4 kinematic envelope.
To maintain stable reclosure within this space, the structural carrier must undergo a specific decomposition. The fundamental representation of SU4 is forced into a 4:3+1 split. This division creates a structural triplet and a singlet, identifying the separation between quarks and leptons. Completing this representation requires tensoring the carrier with two equivalent endpoints, creating a two-dimensional multiplicity space. This leads to a primary observation: the replication of matter into three distinct generations. The framework derives this count through a rank-nullity argument. A mathematical map projects the two-dimensional endpoint source into a three-dimensional generation carrier. Under generic rank 2 conditions, mapping a two-dimensional plane into a three-dimensional volume leaves exactly one orthogonal dimension untouched. This geometry yields exactly 3 dimensions, 2 sourced planes and 1 residual line. This count is the mathematical minimum required to support a Dirac mixing phase for CP violation. The existence of exactly 3 generations is a topological outcome of rank 2 geometric closure. These derivations must be tethered to physical data. A framework of this scope requires strict falsifiability. This is tested through the reclosure loop's dual mathematical burden. First, derive effective local laws from global constraints. Second, executing standard dynamics on those sectors must successfully reproduce observed reality. If the model kills flavor structure or requires hand-inserted invariants, it is falsified. The survival of the framework depends on its ability to match the exact data recorded in particle accelerators. We see how an unresolved continuum systematically restricts itself into the stable constraints of the standard model. Physical reality is the invariant geometry surviving this perversive progression. The local equations measured in our colliders represent the final, irreducible stage of this process.